All right, so an important thing to take into consideration when we do the equations of motion for the ocean is the fact that we want to describe the ocean relative to a coordinate system that is fixed with the Earth, so that it spins along with the Earth in terms of an absolute frame. And that means that there's going to be some, if you were standing somewhere not on the Earth and you were fixed, it would appear that the coordinate axes are turning with time according to the spin of the Earth, and that will give some, when we write down the acceleration of position vectors, or the velocity and the acceleration of position vectors in the rotating frame, we're going to have to take into account these extra accelerations that come about from the fact that the coordinate frame is rotating. And that's important because Newton's equation, F equals ma, applies to an inertial frame, which means a frame that's not accelerating. But when we try to use Newton's equation on Earth, we are in an accelerating frame, right? One that's changing direction and spinning all the time. And so what we do is we write down the acceleration in an inertial frame, and then we'll get these extra acceleration terms that come from the fact that the coordinate system is rotating on Earth, and we interpret these as forces in the rotating coordinate frame. And these forces are the centrifugal and the Coriolis acceleration. So the plan for this lecture is going to be, first we're going to take an arbitrary vector and find out what its time derivative is, a fixed vector that's fixed in the rotating frame, so it's spinning, and we're going to find out what's its time derivative in an inertial frame. And then we're going to take the derivative again of that vector. Then we're going to imagine a vector that's not fixed in the rotating frame, but a vector that's moving in the rotating frame, take its derivative and find out what its time rate of change is from the point of view of somebody which is not rotating with the Earth. And then we'll take the derivative again and get the acceleration. So we're going to do this in 3 steps. So the first part is we're going to imagine that I'm the spin axis of the Earth. So if this is the Earth, right, and this is the Earth is rotating about this axis this way. This is the equator. The way we describe the rotation is we're going to describe it in terms of a vector, right? So we're going to align it with the rotation with the spin axis, right? So the Earth is spinning in this direction. It's not spinning with respect to another axis. That would be a different type of rotation. So there's a particular direction to the spin of the Earth, which is given by the axis, the spin axis of the Earth. And there's also a magnitude to it, right? The Earth does one full turn every day. So we're going to describe using a vector, omega, and that vector has a magnitude, omega, and a direction, omega hat, and the direction, omega hat, is given by a unit vector aligned with the spin axis of the Earth. And of course there's 2 choices. We can align it so that it points towards the North Pole or the South Pole. The convention is that the spin axis, the omega hat vector points towards the North Pole if you put it at the center of the Earth. So it's pointing in that direction. That's an arbitrary choice that we made. And the magnitude of that vector is the rotation rate. So we define it to be 2 pi in 1 day times omega hat. So that's the rotation vector for the Earth, the spin vector. Okay, so now I'll go back to my picture. So suppose I'm the spin axis of the Earth and I'm spinning at a rate of 1 turn per day, right? And now I'm going to imagine that there's a vector, q, that's my arm, and it rotates with respect to the absolute space, but with respect to somebody standing on the Earth, somebody sitting on my big belly here, that vector is not changing with time, right? So it's rotating around like this. So if you're standing on the Earth, that vector, my arm, is not changing with time. Of course, it is changing. It's drawing out a circle as the Earth spins, right? From the point of view of somebody who's not rotating with the Earth. And so this vector here, which is pointing out here, we can break it down into 2 parts. So we can break it out into one component, which is along the spin axis. So one component pointing up like my body, and then another part which is perpendicular to that, which is the projection onto the floor of my arm, right? So we have 2 parts. One is perpendicular to the spin axis. We're going to call that Q perpendicular. This is Q, and then the part along the spin axis, Q parallel. So we're going to write the following. We have a vector q, and we're going to write it as q parallel plus q perp. So these two vectors are perpendicular to each other. So q perp dotted with q parallel is 0. And the q parallel, right, this is the omega hat in this direction, and this is q. And if we project onto this direction, this will be q parallel. And so the way we get q parallel, it's going to be equal to q dotted with omega hat, and it's going to be in the direction of omega hat. That's q parallel, plus q perpendicular is going to be in this direction. This will be q perpendicular, and q perpendicular is just going to be q minus q parallel, right? That's the definition. If I subtract q parallel, I get q perpendicular. So it will be q minus q parallel, and that is equal to, then I can sub in, I get q dotted with omega hat plus q minus q parallel, which was this part, q dotted with omega hat times omega hat. All right, so I've decomposed q into q parallel, write it out again, which is q hat dot omega hat, q vector dotted with omega hat times omega hat. This is the part parallel to the spin axis, and one which is perpendicular to that, which is equal to q minus q hat dot omega hat. Okay, so now I want to find out what is the time rate of change of q from the point of view of an inertial frame, one that's not rotating with the Earth, right? Because remember, q is spinning, right? Q is spinning, and it's drawing out the tip of it, the projection of the tip onto the floor is drawing out a circle. But before I can describe that, I have these two vectors, q parallel and q perp. So I have two directions. In space, we need, in general, there's three directions. So I'm going to define a third direction, b, right, which is going to be perpendicular to these two vectors. So I will define the third direction to be given by the cross product of those two vectors. So it will be the cross product of, to make it easier, the cross product of b, you draw my picture again, and omega hat. So if this is omega hat, and this is the vector q, right? I have q perp in this direction. I have q parallel in this direction, and then the b is going to be into the board. So it's going to be given by the cross product of q and omega hat. So it'll be the cross product of omega hat cross q. If I use the right-hand rule, right, if I do omega cross q, so when I want to do the cross product to find out the direction, it's going to be, what I do is I sweep omega into q, and then my thumb points in the direction that it's going. Right, so it's the right-hand rule. Right? If I use a left hand, it would go the other way. So remember the right hand. So it's pointing into the board. So that's the direction of B. And the magnitude of this cross product, if you don't remember, the magnitude of this is going to be B. Magnitude of B is the magnitude of omega hat times the magnitude of Q times the sine of the angle between these two vectors. So if this is omega hat, this is Q, this angle is theta, this is Q perp, this is Q parallel, and the magnitude of this one is sine of theta. So it's defined, the magnitude of B is defined as the area swept out by the parallelogram by omega hat and B. So if I completed the parallelogram, this area is the size of B. So in the limit where sine theta goes to 0, the area goes to 0. Sorry, yeah, where theta goes to 0, sine of theta goes to 0, and b goes to 0. So it's going to be a maximum when omega hat and q hat are perpendicular. So the way to remember is that you get sine of theta when you do the cross product, you get cosine of theta when you do the dot product, right? So the cross product gives you another vector, and the magnitude scales the sine of the angle between them. The dot product gives you a scalar, and its magnitude goes like the cosine of the angle between them. Okay, so now I have my new coordinate system here, and I can try to figure out what's going to happen to q as it changes with time, right? Q is rotating here. So what I want to show is, let me erase all this and show a plane here. So I have a plane, and in this direction I have q perpendicular, and in this direction I have b. So the omega hat here is pointing out of the board, right? It's coming out of the board, and this is the vector b. And as time, so the projection of q onto this plane spanned by b and q perp is going to be here at time 0, and as time goes on, it's going to trace out a circle, right? Does that look like a circle? Not really. That's better. And this is where the q perp will be at some later time, t plus delta t, at this time t. And this angle, well, if it the time between this and this is delta t, and remember the vector is rotating at a rate omega, so this angle here is omega delta t. And so we want to express q in terms of q perp, at times t plus delta t in terms of q perp at time t, and so that I could take the difference between these two vectors and then calculate what the derivative of q perp is as a function of time. So q perpendicular at times t plus delta t is going to be equal to, so there's going to be a projection down here onto q perp, right? And the projection will go like the cosine of omega delta t. So it will be cosine of omega delta t, q perp of t. And there will also be a part in this direction, right? That projects onto b, and plus, and that one will go like the sine of omega delta t. So sine of omega delta t times b. Yes, and now I'm going to subtract q of t from both sides, and then I'm going to take the limit as delta t goes to 0. All right, and that will give me the derivative. So let me erase this here and write that up here. So if I subtract q, oh sorry, that's q perp. If I subtract q perp from both sides of the equation, I get q perp at times t plus delta t minus q perp at times t. And on this side, if I subtract q perp, I'll get cos minus 1. So I'll get cosine of omega delta t minus 1 times q perp at times t, and plus sine of omega delta t times b. And then again, remember I'm going to divide by delta t, divide by delta t, by delta t, and then I want to take the limit as delta t goes to 0. So if I take the limit as delta t goes to 0 gives, right, on this side, I'll just get the time derivative of q perp, right? d by dt of q perp, right? That's the definition of the derivative. And on this side, I will get, so as delta t goes to 0, the denominator will go to 0. The numerator, the cosine will go to 1, so 1 minus 1 is 0, so I'll get 0 over 0. So this is an opportunity to use L'Hopital's rule that you learned from calculus in high school or in your first year calculus class. So when we have this 0 over 0 limit, the limit is equal to the limit of the derivative of the top divided by the derivative of the bottom. So that will give me the limit as delta t goes to 0. So the derivative of the top is going to be minus omega sine of omega delta t. Derivative of 1 is 0, and the derivative of delta t with respect to delta t is just 1 times q perp of t. And for this term, we have the same business going on. As delta t goes to 0, the numerator will go to 0, and the denominator will go to 0. So again, we can use L'Hopital's rule, take the derivative of the top, take the derivative of the bottom, and then take the limit. So that's going to be plus, so the derivative of the top is omega cosine of omega delta t, and the derivative of delta t with respect to delta t is just 1 times b. And now we're in business. Now we can take the limits. So the limit of sine as delta t goes to 0 will just be 0, so the first term vanishes. The second term, the limit of cosine as delta t goes to 0 is 1. So this will be omega b, this limit. So what I get is omega times b. Okay, so the derivative is just omega b. Right, so it's, that kind of makes sense, right? If I have omega, right, and as I'm spinning, right, the direction in which it moves, right, is in the direction that's perpendicular to q in the spin axis. It's the change is in this direction, right, in the direction of b, which is perpendicular to the spin axis in q. And of course, the size, the rate at which it changes, has to be proportional to omega, right? In the limit where omega goes to 0, the derivative of q perp would be 0, so that makes sense. That would scale as omega. Anyways, we've derived it exactly, so that is the derivative of q perp. We can also do the derivative of q parallel, right? d by dt of q parallel, right? What's that going to be equal to? That will be 0, right? Because the parallel part, the vector, is along the spin axis. As I spin, that vector doesn't change. It's always pointing in the same direction, and its size doesn't change. So this will just be 0. So the q parallel part doesn't change. And since the q itself is equal to the sum of this plus that, we now know what the derivative of q is, right? It's equal to derivative of these two terms. So what we get is the following. The derivative of a vector, d by dt, of a vector which, an arbitrary vector in the rotating frame, is equal to the derivative of q perp plus q parallel, and the derivative of parallel is 0. The derivative of q perp is omega b, so that's equal to omega b. And remember b, what was b? It is omega hat cross q. And what is omega times omega hat? That's our original omega. So this is equal to the vector omega times cross q hat, right? Remember, omega is equal to omega times omega hat. This is the direction, and this is the magnitude, 2 pi per day. All right, use this rule to find out what's the derivative of my coordinate vectors. So, right, d by dt of x hat is going to be omega cross x hat. And d by dt of y hat is going to be omega cross y hat. And d by dt of z hat, you guessed it, is omega cross z hat. So that's convenient, because now if I pick an arbitrary vector, p, right, and I make it a function of time, even in the rotating coordinate frame, then I can describe it as x of t times x hat. So x tells us how the point p, the vector p, how its x component changes with time. But x hat, remember, is fixed in the rotating frame, but it's rotating in the inertial frame, and its rate of change in the fixed frame is given by this expression. Plus y of t times y hat plus z of t times z hat. So this is some arbitrary vector that is changing in the rotating frame. And v's is how it changes with respect to some coordinate axis in the rotating frame. Okay, so now we're going to take the derivative of this thing and find out what's the time rate of change of this thing. So if I take d by dt of p of t, what I get is, I'm going to use the product rule, will be x dot, so that's the time rate of change of this x coordinate, times x hat, plus x times dx hat dt, plus y dot times y hat, plus y dy hat dt, plus z dot z hat, plus z dz hat dt. And now I'm going to combine these three terms. So what I get is x dot x hat plus y dot y hat plus z dot z hat. That's this, this, plus this. And then these terms plus, I'm going to replace dx hat dt by what its derivative is, right? Remember, that's omega cross x hat. So this is going to be x times omega cross x hat plus y times omega cross y hat plus z omega cross z hat. And these are vector omegas. And so what's this first part? This looks like what somebody on the Earth, on the rotating frame, would think is the velocity of p, right? That's the speed, the rate at which p moves. Because remember, x hat, y hat, and z hat, they're fixed in their rotating frame. And this is how its coordinates, how the point is moving relative to its coordinate system. So this first part here is the velocity, but it's the velocity in the rotating frame. So to remind us of this, I'll just put a little rotation here. That's the velocity. And it could be a function of time in general. And then the other part, plus, will be omega cross, and then I could bring the x's just a scalar inside, and I can combine the three-part x times x hat, x times x hat, plus y times y hat, plus z times z hat. And so what we get is just v, rotation, the speed in the rotating frame, plus omega, this vector of rotation for the Earth crossed, and this is just the original p vector over here, p. All right, so now I know what is the time rate of change of a point that's moving relative to the Earth, what its time rate of change is in an inertial frame or non-rotating. There's two parts. There's the velocity with respect to the Earth, which is rotating, or with respect to the rotating coordinate frame, v rotation. But there's an extra part, which is omega cross p, right? And that omega cross p is just the extra velocity that we have because the point is moving because the Earth is moving. Okay, so now I have derived, I guess, a very long-winded way, what is dp dt? It's equal to v in the rotating frame plus omega cross p. Now we're going to take the derivative again of this to get the acceleration, right? So now I'm going to do this again, but this time we're going to do it to get the second derivative. So if I take the second derivative, d by dt of dp dt, that's the second derivative, p, that will be equal to d by dt of v rotation omega cross p. And I can rewrite it out like this, which is d by dt of x dot x hat plus y dot y hat plus z dot z hat, that's v rotation, plus omega cross x hat plus y hat plus z hat, d by dt of this whole business. All right, and we'll just use the product rule and expand this out and see what we get. So I'll get x double dot x hat plus x dot dx hat dt plus y double dot y hat plus y dot dy hat dt plus z double dot z hat plus z dot times dz hat dt. So that's the product rule applied to these three terms. And we keep going on to this side. So omega is a constant vector. This is vector, vector, vector. But this time here, I'll get a time rate of change of that one. X double dot x hat plus y double dot y hat plus z double dot z hat. Right, this is just going to look like the acceleration in the rotating frame, plus, and I have these terms here, right? X dot dx hat dt, y dot dy hat dt, z dot dz hat dt. And so that will be
x hat, I can just combine, right? We just did it around, the same thing as around, will be omega cross x dot x hat plus y dot y hat plus z dot z hat.
That's what I get from this term plus this term plus this term is omega cross x dot x hat plus y dot y hat plus z dot z hat. Right, I just used the fact that dx hat dt is omega cross x hat. And then I brought the x dot inside, the y dot inside. Okay, so that takes care of the first line. And then I have the second line, and I'm running out of space. Let me copy plus to be continued, because I'm running out of space. I'm going to erase everything up here. So what do I have? I have the second derivative, d2p dt is equal to the acceleration, this term, a in the rotating frame, plus omega cross, this is a vector omega, cross with this just looks like the velocity in the rotating frame, v in the rotating frame, plus, then I have the last line here, or the second line, plus omega cross, and on the inside, what if I combine this, right? These three terms, that's just the velocity in the rotating frame. So v in the rotating frame, plus this bit, right? X dx hat dt, y dy hat dt, z dz hat dt. And those three terms, we've done it before, that's just omega cross p, plus omega cross p. All right, so it's starting to look good. And what we have is a in the rotating frame plus omega cross v in the rotating frame plus, and now I'm going to distribute omega cross v in the rotating frame plus omega crossed with omega crossed with p. These two are the same, I can combine them. So a in the rotating frame plus 2 omega cross v in the rotating frame plus omega cross p. All right, and now I can figure out what the acceleration in the rotating frame is from the point of view of an inertial frame, right? So I can solve. So I can say that a in the rotating frame is equal to the acceleration in an inertial frame, d2p dt, minus 2 omega cross v in the rotating frame, minus omega cross p. And I guess this is the acceleration in the rotating frame, so I'll write it like this, d2p dt squared in the rotating frame. So this is the final result. It says that the acceleration in the rotating frame is equal to the acceleration in the inertial frame, but there's some corrections. And there's namely this one, which goes like 2 omega cross v rotation. This one is known as the Coriolis acceleration, right? And it vanishes for things that are not moving, right? If the velocity of the point P is 0, then v rotation is 0, 0 in the rotating frame, then this Coriolis force or Coriolis acceleration vanishes. And then the other one that goes like omega cross P, that's our friend, the centrifugal acceleration. So let's see if this has the right sign, right? So remember my vector P, let's say this is my vector P, and for simplicity, let's assume P is not changing with time on the rotating frame. So it's spinning around, right? So the centrifugal, right, is going to try to fling it outwards, right? So it should be, if this is the Earth, like this, and this is omega is going this way, we have a point, and this is the center of the Earth, I have a point out here. The centrifugal force should be pointing away, right, from the axis of rotation, right? It should be pointing out here. Omega, or minus omega cross P, and this is the vector P. Should be pointing out that way. So let's check that that's the case. So if I do omega cross P, right? Omega is the vertical, like my head, and then I sweep it into P. So it's pointing in the direction of my thumb, which is into the board, right? So the first, this vector omega cross P is now pointing in the direction of the board. Right, so if now I look down on the Earth from looking down on the North Pole, this is the North Pole, then the omega cross P, right, is in this direction. And P, remember, was the projection of it in the equatorial plane was in this direction, P perp. We're looking down around the North Pole. This is omega cross P is into the board or looking down, it's in this direction. And now I'm going to do omega, which is pointing out of the board, cross omega cross P. So again, the right hand rule, I sweep omega, this is vector, omega onto this one, and the direction of my thumb gives me the direction, so it should be pointing perpendicular in this direction. So this is omega cross P, which is the opposite direction of what we said, right? The centrifugal should be out, but remember there's a minus sign, right? There's that minus, and so it's pointing outwards. So that all checks out. So this is indeed trying to, it's compensating for the centripetal acceleration, which is gravity, right? Gravity keeps us stuck to the Earth, so there's a force, a real force from gravity that keeps us on the surface of the Earth, and then the centrifugal acceleration comes from the fact that we're in a rotating frame, which would fling it off the surface of the Earth, is pointing outwards. And so the centrifugal and the centripetal, they balance each other. Centrifugal, Coriolis, acceleration in an inertial frame. So if I apply Newton's second law, right, it applies to this one. If I want to apply it to this one, I'll have these extra acceleration terms that I have to take into account. So this is the acceleration in the inertial frame. This one is the Coriolis acceleration, and this one is the centrifugal acceleration. Well, I guess we should all also check out what is the direction of this one, right? Omega cross V. So suppose that my point V, my vector P is moving. Suppose it's moving in this direction, right? So as the Earth moves, this one is moving a little bit faster than me. So I'm spinning around, but this one's moving a little bit faster. So this Coriolis acceleration should be omega cross V. So if I'm moving a little bit faster in the direction of my thumb, the velocity is in the direction of my thumb, and so it's pointing out at me. Omega, remember, is in the direction of me, so if I do omega cross V, it will go in this direction, in the direction of my right hand thumb now, right? V is in this direction, omega cross V is in this direction, and so it's pointing in the direction so I have to relate it relative to velocity. So the velocity is in this direction, it's perpendicular to the velocity, right? And it points to omega cross v points to the left, but minus omega cross v points to the right of the direction of motion. So if I'm moving in this direction, the Coriolis force, or the Coriolis acceleration, will accelerate me to the right of the direction I'm moving. So that's in the northern hemisphere, right? Because I picked omega to be that way. So if I'm walking in this direction, there's going to be a Coriolis acceleration pushing me perpendicular to the direction I'm going, to the right in the northern hemisphere. To the left in the southern hemisphere, because I'm going to be upside down on the other side of the Earth. Okay, that's long enough for the acceleration of centrifugal and Coriolis. Let's stop.